Hi everybody. Today we're going to start talking about uniformly accelerated motion in another direction, the vertical direction. We're going to start talking about free fall. Now you might use the term free fall already if you think about somebody jumping out of an airplane with a parachute. But please remember that when we start to talk about terms that we use in the real world in science class, sometimes they have more specific meaning than science class. So our objectives for this lesson are to define free fall motion, to define the acceleration due to gravity, and then to be able to solve problems for objects in free fall motion. So let's look at free fall. We all know that if we have something in our hand, an object in our hand, and we take our hand away, that object will fall to the ground. That happens because the Earth exerts a force due to gravity on that object, and that causes the object to move towards the center of the Earth or the surface of the Earth or towards the ground, however you want to think about it. Now, Galileo found out for us several hundred years ago that all objects fall to the ground at the same rate. Now, that might not seem to fit with you. If you think about a hammer and a feather there, for example, if you had them each in your hand and dropped them, you're going to say that they fall differently to the surface of the Earth. The hammer would hit the ground a lot quicker than the feather. Well, the reason that that happens here on Earth is because of air. That resistance that the air provides slows down the feather more than it does the hammer. So if we take away air, we give ourselves an environment that is a vacuum, we can ignore air, and then we can see that those objects will all travel the same way at the same constant acceleration towards the surface or the center of the Earth. And again, you may say that you're not really sure about that, but we're actually going to watch a video of an astronaut dropping a hammer and a feather on the surface of the moon where there is no atmosphere or no air, and they actually do hit the ground at the same time. So when an object falls through the air only under the influence of gravity, so it's not in your hand, it's not connected by a string, it's not hanging from a wire, and we ignore air resistance, we call that motion free fall. So if those objects that are in free fall all move at the same rate, what is that rate? Well, that rate is the acceleration due to gravity. The acceleration due to gravity is the acceleration that the object in free fall motion experiences when it's in motion. It has a special symbol when we talk about the acceleration due to gravity, and the special symbol is the lowercase letter g. Remember back to the beginning of the year when we started talking about variables and variable letters, and I said there was a difference between big G and little g, or big M and little m. And you have to be really careful about which you use, because some constant variables we use certain letters for, and we need to know what we're talking about. So when we see something that is little g, we know that we're talking about an acceleration due to gravity. Now on Earth, that acceleration due to gravity is 9.8 meters per second squared. That means when we neglect air resistance, when we drop something, that object accelerates at a rate of 9.8 meters per second every second. The value of g can change depending on where you are, because it has to do with the size of the force of gravity. But we're always going to use 9.8 meters per second squared because our objects are usually on the surface of the Earth. Now remember, acceleration is a vector, so is g, so we have to be able to not only define its size, but its direction. So remember, acceleration can be positive or negative in your problem depending upon your coordinate system. So here's what I'm going to do in class. I'm going to say that downward is the negative direction and upward is the positive direction, just like the y-axis, negative and positive direction. So that means for me that since gravity is always going to accelerate objects downward, always going to pull it towards the surface or the center of the Earth, my g is always going to be negative. So g for me is always going to be negative 9.8 meters per second squared. That also means that any velocity or any displacement defined as going downwards is also negative. Now you can take g as positive. So you could say that downward direction is positive, which would mean any velocity or any displacement in the downward direction is positive, but then that means that anything going upwards has to be negative, and that tends to confuse us. So as a result for me, remember that I'm always going to say that g is equal to negative 9.8 meters per second squared. Now, free fall motion is uniformly accelerated motion. The acceleration is constant during the whole period of motion. The velocity is changing its velocity, or the object is changing its velocity by a constant rate. So since that's true, it's just like what we've done in horizontal motion. Those kinematic equations can be used to describe free-falling objects simply because it's also uniformly accelerated motion. So any of those equations that we've already been using for horizontal motion, cars on roads, people walking, all those examples that we've been using, can get rewritten, if you like, to replace the acceleration value with g. So instead you can replace a for acceleration with g if you would like. It actually makes it easier for us to do these types of problems because we never have to calculate acceleration. We know that the acceleration value is always equal to g. There are two types of freefall motion that we're going to consider. In the first type, we're going to have an object dropped from an elevated height which falls to the ground. So if it's dropped, remember that's sort of like an object starting at rest. So as a result, that tells us that the initial velocity is going to be 0 meters per second. So if you look at the picture here, you notice it's 0 meters per second, that velocity is 0, and as the object falls, its velocity increases or it speeds up, and we are now changing the amount we travel every second. So because we're going faster and faster every second, we're also traveling more and more distance every second. Now sometimes it helps to look at that graph information in order to understand the motion too. So you can see here, if we take our velocity versus time information for this rock being dropped, we start off at time equals 0, our velocity is equal to 0. As we speed up our velocity, all right, the size of our velocity, our speed gets bigger and bigger, but in the negative direction, because I'm taking down to be in the negative direction. You can see that the sign of our velocity during motion is negative, and the slope of the line of the velocity versus time graph, the acceleration, is also negative. So as a result, our velocity and our acceleration have the same signs, both negative, and our object is speeding up as it moves towards the ground. The other type of freefall motion that we're going to consider is when an object is thrown directly upwards into the air, and then it stops for an instant and comes back down again. So what's happening here is you're throwing up an object, a rock or a ball, with an initial velocity. So that's the fastest that object's ever going to be going, because as it travels upwards, gravity is slowing it down. It slows it down all the way until all the way at that peak or that top point. The velocity is 0, and then it turns it around and the ball travels back down again and speeds up as it comes back down again. And actually, this is a very good example of how we're going to be able to use this information. Our motion is very symmetric. Whatever velocity our ball leaves our hand with, or the speed it leaves it with going in the positive direction, it's going to have that same speed when it's at the same position coming back down again, just in the negative direction. And that has to do with that symmetry of that relationship, because the only thing that's affecting the motion is gravity. So gravity slows it down as it goes up, gravity speeds it up as it comes down, because remember, anything that goes up must come down. So what's actually happening with this type of motion is as the object travels upwards, gravity slows the velocity until it's 0 meters per second for that instant when the ball is all the way at the peak of its motion, the highest point of its motion. At that point, just because velocity is 0 does not mean acceleration goes away. Gravity always exists. It does not turn off for an instant and come back on again. Instead, what's happening at that peak is acceleration is changing the direction of the motion. Because remember, acceleration can exist if velocity changes in its speed, in its direction, or both. So always remember, as something goes up and then comes back down again, at that peak, its velocity is 0 meters per second, but gravity has not gone away. Instead, gravity is just causing the ball or the object to accelerate, and the acceleration is just causing a change in direction of motion. Let's look at a velocity versus time graph for this type of motion. So if we look at it, again, if I consider my upward direction to be positive and my downward direction to be negative, when the ball is thrown up, the instant it leaves my hand is when it has its greatest velocity. It's a positive velocity because it's going upwards. As it travels up in the air, gravity slows it down, so the velocity gets less and less and less. And that's making sense because my velocity is positive, but the slope of the line of my velocity versus time graph, the acceleration is negative. So my velocity and my acceleration have opposite signs, which means I'm slowing down. I get to this peak right here, which is where my velocity is 0 right here. Does not mean that the acceleration goes away. So you see that line is still there. So the acceleration due to gravity still exists. It's just at that peak, it's turning the direction or changing the direction so that the velocity is now becoming negative. Remember, that's how we can tell whether or not we've changed direction. Our velocity has to change signs, and that's what happens here. So now, as the ball comes back down again, our velocity is becoming more and more negative, which simply means it's speeding up in the negative direction. Again, if we look at our velocity as negative, the slope of the velocity versus time graph, or the acceleration, is negative. My velocity and my acceleration have the same signs. I am speeding up. And that makes sense with what we see when we throw something up in the air and it comes back down again. So as a result, when we start to talk about free fall, remember that free fall means that an object is traveling only under the influence of gravity through the air. Nothing else is touching it, not your hand, not a string, it's not sitting on a table. We neglect air resistance. When we start to talk about objects on the surface of the earth or near the surface of the earth, that value of the acceleration that it experiences due to gravity is 9.8 meters per second squared. I'm going to say in a down direction, so it'll always be negative 9.8 meters per second squared if I consider my down direction to be negative. And last but not least, when we want to solve problems, looking at the motion of the object as it travels through the air, we can still use our kinematic equations for motion that we use for horizontal motion. We just know the value of acceleration. So any place that you've been using A in those equations, you can now replace with the value of G.